Hello and welcome. I'm Bob Falconer. This is the second in the series of presentations about the MARFLEX system of masonry bridge repair and strengthening. The first presentation showed the purpose of the components of the system and how they are interrelated. It also gave an example of costs and examined the environmental advantages of the system. I've split this presentation into two parts, A and B, in order to keep each one to a sensible length. In this part A of the second presentation, we will look at some completed bridge case studies to illustrate the use of the MARFLEX system. As I said in the previous video, I am a director of Goldhawk Bridge Restoration Limited, the company that installs the system, though I will be giving a personal perspective rather than a company one. We've got a lot to get through, so I'll get straight into it. The first case study is a Great Western Railway bridge designed by Brunel and built in 1847. The 3.45 metre span bridge has to carry heavy aggregate trains and was exhibiting deflections of around 10 millimetres at the crown under load. When you're carrying out a preliminary inspection like this, a simple deflection pole is a good way of getting a feel for the behaviour of the bridge. There's the deflection pole and there is me. Our MD took the photo. He clearly thought that the back of my head was a better proposition to the front. An aggregate train tends to pass over about 11 o'clock every morning, and it was actually quite frightening standing under the bridge when this went over. Previous inspection reports concluded that the barrel was deformed, but we were able to fit the profile of a three-centred, or if you like, pseudo-elliptical profile to the barrel, and concluded it was designed like this in the first place. It's very near Brunel's Maidenhead Bridge in any case. First thoughts are that it's not really a very sensible design from Mr. Brunel. He should have been Lord Brunel, as pseudo-elliptical barrels rely heavily on backing behind the springings, and it's difficult to achieve this in a tall structure within an embankment. A semicircular barrel would have relied less on support from the backing. However, a semicircular barrel would have behaved more like a jelly mould than the pseudo-elliptical barrel, which only seemed to exhibit vertical movement at the crown. We normally think of masonry arch barrels as being non-linear, but this barrel was perfectly linear in that after repetitive large deflections from the aggregate train, always returned to zero after each axle passed over it. Not much is written about the responses of different barrel profiles, and I think this might be something worthy of further investigation. Also, there's a big difference between the effects of railway loading and that of HGVs on highways. There's more vibration from railway loading and it's much more cyclical. This again would be worthy of further investigation. Bridges like this form a hard spot in the embankment which settles around the structure. Thus, the effectiveness of the backing gets lost. An illustration of this is the platform at my local station. A similar structure runs under the platform, under there, and the settlement around the hard spot can clearly be seen. A system of soft propping, shown there, designed by Arcadis, was installed during the works. This was insulated from the barrel by a 25mm elastomeric strip, which gave reassurance to our installers that the bridge wouldn't fall around their ears whilst the heavy freight trains were travelling over. This wasn't actually necessary, as the system had been designed to be stable whilst the rebars were being installed. The movement under load after the propping had been installed was 6mm, as you can see from the monitoring. In order to strengthen the backing, we used the Reforce system of foundation strengthening, patented by our sister company, Stress UK. There's nothing new about grouting backing, but this is the first time the Reforce system was used for a purpose other than strengthening foundations. This system enables grout to be placed with great accuracy, and we were thus able to prevent bleeding of the grout into the track bed. The grout used was a low viscosity hydroreactive geopolymer resin. The reinforced system on its own reduced the soft prop deflection by just under 50%. The MARFLEX system was designed to reduce the deflection for the heaviest freight trains to 2.34 millimeters. In the end, after the MARFLEX system became effective, the maximum measured unpropped deflection was 1.25 millimeters, a considerable reduction from the original measured 10 millimeters, as we can see here. There's a big difference between the graphs. There were 6 XY deflection monitoring stations fixed to the intrados of the barrel. It should be noted that our solution shouldn't be regarded as a permanent one. The inserted backing will, through time, begin to settle away from the barrel. I would estimate that the grouting will need to be refreshed after, say, about 50 years. The finished bridge, here, looks good, and now it doesn't exhibit the alarming deflections that it did before we installed our remedial works. I should say that there's no way that Brunel could have foreseen the weight of the trains that would be using his bridge, which would still be perfectly adequate today in carrying the trains of his day. We have just strengthened his design to bring the bridge up to modern standards. The Mars installation avoided closing the busy railway line and the great expense of an unenvironmentally friendly concrete arch, which was the alternative proposal. It also avoided the criminal destruction of Brunel's legacy. The next case study is an 8.5 metre span canal bridge in the centre of Birmingham. The bridge is constructed in 3 sections side by side, 2 masonry arches that you can see, and an unseen jack arch bridge in the background. The barrel in the foreground had to be strengthened to carry the Midland Metro tram system along Broad Street. As can be seen, the adjacent barrel had been strengthened using a concrete arch liner, which we can see there. In order to retain the well-used towpaths, this entailed narrowing of the canal and the construction of new towpaths in the canal. It also created quite a dangerous obstacle for pedestrians on their mobile phones. I have no idea how much all this cost, not only in terms of finance, but in terms of environmental cost. The completed Mars installation can be seen in the foreground, which is here. This retained the full width of the canal and no alterations to the towpath. I had a friend who sailed through in his narrowboat. I asked him what he thought of our work. He remembered the concrete line section, but missed our section. The barrel was actually elliptical, built of stepped construction, as we can see. And it was confirmed by exploratory trenches above. We can see the steps. Our analysis was able to take these steps into account. The next case study is a Grade 2 listed Oundle North Bridge in Northamptonshire. This has 13 spans ranging from 3.5 metres to 6.2 metres. It dates back to at least the 14th century and has been much modified since then. The bridge was in a poor state with a 3-ton weight restriction, and we were required to increase the capacity to 44 tons plus SV100 loading. The job didn't start well. The contract start was delayed by flooding. One of our chaps took this photo whilst he was flying over. And then we were hit by that's the photo there of the flooding, and then we were hit by the COVID pandemic. We employed extremely strict working practices, individual vans for each employee, separation of individual tools and PPE, separation of the use of canteen facilities, etc., etc. We bought air-fed hard hats for the site staff. These were actually a boon, as the summer was very hot and the helmets kept the guys cool during the hot weather. There are several forms of construction across the width of the bridge. Some spans required strengthening and others didn't, but all required individual consideration. The Gothic arch shown here didn't need strengthening, and this was the oldest surviving part of the bridge. The neatness of the completed barrel here, as we can see, shows the tremendous skill of our site team, and the fact that we finished on time and to budget shows the dedication of our team. Increasing the capacity by this amount requires careful consideration of the foundation capacity. We thus calculate the increase in foundation pressure for each pier and abutment. We generally consider that an increase of up to 15% is acceptable. Any more than this, then we recommend specific monitoring at principal inspections. This part here. If settlement is detected, then the Reforce foundation rescue system of our sister company Stress UK can be employed. The next case study is another Grade 2 listed structure at Thrapston in Northamptonshire. This had a 7.5 ton weight restriction and required strengthening to full highway plus SV80 loading. This bridge is narrow with one-way traffic controlled working. It dates back to before the 13th century and now comprises 9 spans ranging from 5 metres to 9 metres. I'll talk while this video is playing. The video was taken by one of our supervisors who's a drone enthusiast. It pans from our compound here, going out to the span where our guys are working, somewhere out here. The main problem with this bridge was an upward rise in the centre of the main navigation span. An accurate point cloud survey of the intrados indicated that the centre of the barrel had risen by about 105 millimetres compared to the edges, which were held in place by the relatively thick spandrel parapet walls. There were significant circumferential cracks parallel to this parapet spandrel walls at about 1.2 metres from each edge. Continuous monitoring of the barrel showed that this span was flexible under load. There was no evidence of significant pier rotation and no reflective movement of the adjacent spans. There was, however, significant rotation at the springing of one of the piers. The barrel had been reconstructed with unbonded brick rings. It was thus concluded that the connection to the piers had moved and the barrel was of insufficient thickness, which we measured by coring. The solution adopted for this span was to anchor the springing and haunches to the piers and reinforce the barrel to bring it up to the required capacity. This photo here shows the care that our heritage masons take over making sure the details look good. We've got some very talented people working for us. Again, not all spans required strengthening. Some spans exhibited ring separation, and in these we only inserted radial pins. Other spans only required a nominal Mars installation to bridge extensive cracking. The video now shows our guys working from a floating pontoon under the main navigation span. The pontoon allows them to move out of the way to anyone who needs to sail under this span. We unusually had to close the bridge to traffic whilst we were working on this span, but it was opened again once we'd finished. Not only are these large bridges a challenge, small bridges can be just as fascinating. This is a small stone bridge in the remote part of Calderdale that had been neglected. You can neglect masonry bridges and they still remain serviceable. Some attempt had been made in the past to strengthen this bridge by introducing extensions to the abutments, here and here, and wrought iron support beams supporting a tray which in turn supported concrete infill over part of the width. The width of the bridge had also been extended at the same time as these support beams had been inserted. The effectiveness of the strengthening works was questionable. There was no backing, and the inserted abutments provided pivot points here and here to the barrel, which would deform away from the back of the inserted abutments, round like that. So all they did was provide pivot points. The inserted wrought iron beams also destroyed the integrity of the barrel, here and here. Furthermore, the works severely reduced the aperture of the bridge, thus encouraging flooding. The bridge had to carry heavy plant to a nearby works, so our solution was to remove the corroded wrought iron support structure, clear that there, and anchor the barrel to the rear of the inserted abutments. It was agreed that removing these abutment extensions wouldn't be cost effective, so we left them in. However, in our design we adopted a span greater than the measured span. The loss of mortar here had allowed some of the voussoirs to drop, and when the wrought iron support structure was removed, it revealed the barrel in a dreadful state. That's the wrought iron support structure. This is the wrought iron beams with the tray, and the concrete infill has been removed, but this barrel was in a dreadful state. We jacked and mortared the voussoirs back into place and installed the designed MAR system. We then installed the anchors to fix the barrel to the rear of the inserted abutments. The finished bridge not only looks good, it can now safely carry the heavy vehicles to the adjacent works area, and also the increased aperture reduces the risk of flooding. This again provided a much more energy saving and cost effective solution to a replacement bridge. This is another bridge in South Wales that had suffered flood damage. In this case, the fill had to be removed before we could jack the barrel back into shape. So the fill has been removed there. We didn't have to remove it from the other side because it was all very well consolidated. The excavation found a concrete filled hard spot over the bulge. I have to say that we find all sorts of materials in the fill over masonry bridges. Some were probably used as 19th century skips, so it makes a bit of a mockery of load distribution methods that are based on perfect fill models studied in the laboratory. It was difficult to achieve a neat installation given the roughness of the barrel surface, but we achieved a serviceable bridge without the financial and environmental cost and the inconvenience of a replacement bridge. This bridge at St Clears in Wales had been strengthened using ugly arch liners. As we can see here, the river had split into two. This was over one part of the bridge, and this is our finished bridge over the other part. In the finished bridge, we removed the liners, well, in both bridges we removed the liners and replaced them with the MAR system. This restored the aperture of the bridge and cured what had been a flooding problem in the area. Masonry bridges rely on loading to work properly. When the loading is removed, then they tend to relax and lose compression in the barrel. This happens when railway lines become redundant. When this frequent compression is lost and the mortar is washed out, rings of brickwork can fall out, as happened in this bridge over the River Wye. You can see the whole ring of brickwork had dropped out. Our role here was to replace the bottom ring. You can see our chaps working there. This replacement ring is merely decorative and doesn't add strength to the barrel, or much strength to the barrel, as no compression had been added to the bricks. The next case study is an 8.45 metre span stone road bridge over the Little Don River in Stockbridge near Sheffield. The bridge had been extended, leaving a barrel comprising 3 sections. See one there? I think there's one there. The original proposal was to replace the bridge, but there was such an outcry from local residents that refurbishment using the MARFLEX system was decided in the end. This photo shows the original bridge under construction. It appears the whole bridge was constructed before the centering was removed. This is the centering here, and that's the completed bridge. As the bridge sank under its self-weight when the centering was removed, cracks would probably have appeared at the time between the spandrel parapet walls, as these would not have sunk as much as the barrel. The centre and early edge sections had a capacity of 3 tons, but the later extension was able to carry full highway loading. It wasn't possible to bring the centre section up to the required loading using the MARFLEX system alone, so it was decided to replace the fill with foamed concrete. The fill over the bridge was removed, as we've seen, and the MARFLEX system installed into the understrength sections of the barrel. This is us setting up the site using floating pontoon again, and that's our finished site setup. Then that shows the final MARFLEX installation. You can see we've strengthened just these 2 sections and brought the bridge back up to full strength. I hope this has given a flavour of the work of Goldhawk Bridge Restoration Limited. The next part of this presentation, Part B, will cover current issues that we're facing, non-bridge and overseas projects. And then the presentation after that will cover the theory, testing and validation of the MARFLEX system. Thank you.